If you add oxone, water, and sodium chloride to Borneol, it will turn into camphor. This video is about how that happens. It happens in 5 steps. In the first step, sodium chloride and oxone turn into a molecule called hypochlorous acid. That's HOCl. The mechanism is called an SN2 mechanism. Let's talk about how that first step happens. The first thing we have to understand is what oxone is. Oxone is 3 separate compounds that are sticking together. When compounds stick together rather than bonding together, they're represented by these dots. So those dots are representing 3 different compounds that are not bonding together but are rather sticking to each other in crystals. Each of these compounds has an SO4 in it. It's easier to see in the 2 compounds on the right. There's also an SO4 here. There's just another oxygen being stuck to it. The way that SO4 looks in these compounds is like this down here. The sulfur is in the middle. It's bonded to 4 oxygens. It's double bonded to 2 of them, single bonded to 2 of them. So this feature here is the SO4 in each of these compounds. So they all have that in common. What's different between them is what else is bonded to that SO4. In the molecule on the right, you have 2 potassiums. And so in this case, these oxygens have negative charges that are being balanced by 2 potassium ions. That's this molecule on the right. In the middle case, you only have 1 potassium, the other one is a hydrogen. So 1 potassium is balancing the negative charge here, and the other has a hydrogen bonded to it. So notice, these 2 compounds are almost identical. And in fact, these 2 compounds are only in the crystal as sort of preservatives to help keep the oxone fresh. The only molecule in oxone that participates in the reaction is this one that I have numbered 1 on the left here. It has an extra oxygen there. So what we're going to add onto the SO4 is an extra oxygen, so that's our 5th oxygen, a hydrogen, and then the potassium on the other side is going to balance out a negative charge on the oxygen there. And this 2 in front just means that you have 2 of these in terms of ratios. You have 2 of them for every one of these other 2 in this crystal that's all getting stuck together. So this is what oxygen, or what oxone, the reagent oxone, looks like chemically. So you can see oxone is just a simple way, a nickname, to refer to this whole conglomeration of ions. So the only thing that's really going to participate in the reaction is this one on the left here, this one that I have numbered number 1. 2 and 3, like I said, are preservatives. So let's take this into another step. This is what is, and I'll just color code this, these charges. This is what is going to react with chlorine. So if you remember in that first step here, oxone reacts with sodium chloride, and specifically with the chlorine in it. Okay. So let's take this. This is going to be one of the characters in the story of this first step, and we're going to mix this with sodium chloride. When you put sodium chloride into solution, the 2 ions separate, the sodium and the chlorine. So they both kind of go their own separate ways. Sodium is enormous. I have a picture of the crystal lattice of sodium chloride here, and you can see how much bigger the sodium is than the chlorine in that crystal lattice. Because sodium is so big, it can spread that positive charge out over a huge volume, and that dilutes the charge and makes sodium very stable. So the sodium is not going to be reactive. It just goes into the solution and bounces around like a billiard ball. Because the chlorine is smaller, it's fitting that negative charge in the smaller space, so it's more sort of potent and reactive. So chlorine here is going to act as our nucleophile, it has a negative charge. And while this large molecule called potassium peroxymonosulfate, although that looks really complicated, conceptually, this is altogether just a big leaving group. Altogether, that's a big leaving group. Because if that were to take electrons on itself, if this were to take these electrons for itself and develop a negative charge on that oxygen, the negative charge would be stabilized through resonance. That lone pair there could be flying around in a p orbital that's parallel with the p orbitals making the pi bonds. And so the negative charge is able to spread out over all of those atoms. Also, the electronegativity of the other oxygens helps to pull that negative charge towards them and spread the charge out even more. And anytime charge gets spread out, it gets stabilized. It gets diluted over space. So conceptually, this whole big group is just a good leaving group. So we have a leaving group here. And all we need is a nucleophile to do a nucleophilic attack on this oxygen. And what you have is nucleophilic attack with loss of a leaving group. That is the definition of an SN2 reaction. So we're going to replace or substitute the leaving group with the nucleophile. And so after this first step, what we're left with is this molecule here. We have this oxygen. The chlorine has attacked it, and the oxygen is also still bonded to this hydrogen. And this is something called hypochlorous acid. This is actually the molecule that's going to react with Borneol in order to turn it into camphor. So in this first step, just to review, in this first step, you do this SN2 reaction with sodium chloride and oxone to get this hypochlorous acid. In the second step, two molecules of hypochlorous acid react together, and one of them gives an H plus to another. So one of the hypochlorous acid molecules gains an H plus from the other and turns into this molecule you can see here. That would be described as a proton transfer. An H plus is really just a proton. Hydrogen only has one proton in its nucleus. So a hydrogen atom is just a proton with an electron going around it. If you take the electron away, all hydrogen is a proton. So when you move an H plus around, you're really just moving a proton around. That's called a proton transfer. And it changes the stability of molecules. So we're going to take this molecule here, this hypochlorous acid, which is stable, and we're going to add an H plus to it. This charge is telling us that this is going to be unstable. So it's sort of like we're hitting the gas pedal for the reaction. It's going to make the reaction happen faster once we have that charge there. So let's look at exactly how that happens in terms of the mechanism. So this is our hypochlorous acid. There are more than one of these in solution. Right? The first step that we saw happens to trillions of molecules, so you end up having trillions of these hypochlorous acid molecules in solution. The oxygens are electronegative, so they have a slightly negative charge. And the hydrogens that they're bonded to are losing electrons. They're not as electronegative as the oxygen, so they have a slightly positive charge. And as these molecules are bouncing around in solution, sometimes the slightly negative oxygen of one will hit the slightly positive hydrogen of another. And that's what causes the proton transfer. The slightly negative oxygen atom steals the hydrogen from another of the molecules the electrons that we're holding on to the oxygen go to the most electronegative place nearby. That's the oxygen on the other molecule there, and this is a proton transfer. We're moving an H plus from one molecule to another. So at the end of this, we'll have one of these with two hydrogens, and now that oxygen would have a full positive charge, which is telling us it's unstable. And then we would, of course, have the other molecule here that's left over. This molecule on the right is not going to participate in our reaction. It's the molecule on the left that's going to participate in our reaction. So in this second step, we take hypochlorous acid. One molecule of hypochlorous acid bumps into another one and steals the H plus from it. That's described as a proton transfer. In the third step, we're going to do another another SN2 reaction. So here, we're finally going to introduce the Borneol, and we're going to put the chlorine onto the Borneol. So in this one, the goal of our last step of adding that H plus was to make this oxygen be a good leaving group. So this is now conceptually our leaving group. All we need is a nucleophile, and we can do an SN2 reaction. And we have a nucleophile on Borneol. It's the slightly negative oxygen atom of the alcohol, the OH. So this oxygen can attack the chlorine, kick the leaving group off. So we have nucleophilic attack, loss of a leaving group. Those are the signatures of a substitution reaction. You're adding one thing, subtracting another, that replaces or substitutes one thing for another. And at the end of this, you would have this now bonded to a chlorine. The oxygen here has a positive charge. Anytime oxygen has 3 bonds, it has a positive charge. And then floating around in the solution is a water molecule. So that's our third step. Our third step is an SN2 reaction where Borneol attacks the chlorine of what was this hypochlorous acid, and the oxygen leaves as a leaving group. So we really put the chlorine onto the oxygen of the isoborneol there. So that's this third step. The fourth step is another proton transfer. If you look at this, this is unstable. That positive charge there is telling you that the molecule is unstable. So we want to stabilize it. We're going to stabilize it by doing a proton transfer, and that will take that positive charge off with the hydrogen that we transfer. So we're going to use the water that we made in the previous step. That water is going to come back, and it will, the slightly negative charge on the oxygen here is what's going to rip off the slightly positive hydrogen here. So this water comes close, it bumps into this, it rips that hydrogen off, the electrons go to the most electronegative place nearby. That's the oxygen. And in this case, the oxygen is really thirsting for electrons because it has that positive charge. And so after you do that proton transfer, that transfer of an H+, you are left with something that looks a lot like Borneol, but where you have a chlorine on the oxygen instead of a hydrogen. So that's this fourth step, this proton transfer to stabilize the Borneol. So if you think about what we've accomplished so far in the 4 steps of the mechanism, all we've really done was we've taken the hydrogen that was on Borneol and we've replaced it with a chlorine. That's what we've done so far. So how do you get this second bond between the carbon and the oxygen? That's the 5th step. You form pi bonds. So the first bond you ever form is a sigma bond. Every bond after that is a pi bond. You form pi bonds like this through elimination reactions. And in this case, you end up doing an E2 reaction. The base in this elimination reaction will be water. So in this last step, you add water to this molecule. And in elimination reactions, you look at the carbon that's next door to the atom that has the leaving group on it. So here, this chlorine is a good leaving group. It's on this oxygen here. Look next door to it. There's a hydrogen on this carbon. Water is going to act as a base and steal that hydrogen. The electrons are going to go toward the oxygen and they kick the chlorine leaving group off. So here we have a proton transfer. Loss of a leaving group. Those are the signature steps for an elimination reaction. And because they're both happening at the same time, it's an E2 reaction. And so, at the end of this, you end up with camphor. The chlorine leaves, this hydrogen is gone, you have the double bond between the carbon and that oxygen. So, looking at this from a sort of bird's eye view, the mechanism for how Borneol turns into camphor when you add oxygen, water, and sodium chloride is first, the sodium chloride and oxone react with each other to give you hypochlorous acid. That happens through an SN2 reaction. Then, 2 hypochlorous acid molecules react together so that one of them steals an H plus from another. When you move H pluses around, that's a proton transfer. It changes stability. Once you have this modified hypochlorous acid molecule, it can react with Borneol. It does an SN2 reaction. The oxygen attacks chlorine, this water group leaves, and you put the chlorine onto isoborneol. Shake that up with the water you have, and you can stabilize it. Get rid of the positive charge by moving the H plus onto the water. And you have this stabilized molecule. Finally, once you have this chlorine leaving group there, you can do an elimination. Water can act as the base, and when it does, you form the second bond between the carbon and the oxygen. And that is the mechanism for how Borneol turns into camphor when you add oxone, water, and sodium chloride.